James. Thanks. Yeah.
Our next speaker is James Sharpnack, who is presenting.
Yeah. Okay, thank you. And thanks to the organizers for their hard work here. So I'll be talking about learning patterns for detection with multiscale scan statistics. So I'll begin with just a description of what the classical multiscale scan statistic is. Okay, so typically it's applied to situations where you're looking for some anomaly in an image. So in this example, this is extracted from a hyperspectral image. This is actually looking for a chemical signature in this hyperspectral image. This was an ordnance explosion that we're seeing right here in this elevated pixel value here. And so in this problem, we're going to be saying, can I detect anything at all in this image? So typically for these problems, if you're saying, let's just try to classify what each pixel corresponds to, that's a classification problem. That's asking the question, what am I seeing? In detection, we're asking the question, do I see anything at all in this image? Okay, so this has many applications. I'll skip over this. Okay, so the scan statistic, the idea is that we're going to take some regular shape, more generally some function, and we're going to convolve our image with that shape, right? And then if, when we average within that shape, if that's abnormally large, then we're going to throw the red flag and say that there is something here. Right? So this in particular, we could specify rectangles, and we could even try it for many different scales, which means different rectangle side lengths. Right? So more generally, we could think of a function, and this could be some function that's actually embedded in a tensor with some noise on top of it. Right? So our tensor is going to be from range from -L to L in d dimensions, and so this is a depiction of a one-dimensional tensor. It's just our vector. And our function is this little wavelet, right? And so these are of course wavelet type filters that we're going to be considering. But it's this little wavelet. It's localized, right? And it's somewhere in this tensor, and we don't know where it is, and we actually don't know its scale. So it could have a long periodicity or a short periodicity. Right? Okay. So we're going to assume a continuous model. Mostly it's for, the continuous part is mostly for mathematical convenience. So before we were talking about images, and those have these discrete pixels, we're just going to think of this as a continuous domain. So there's some pattern F, and we're going to assume it lies within some known class of patterns, capital F. And this pattern, we're going to say it's over -1 to 1. And then it has 2 norm of 1. So this 2 norm of 1 is just making it so that we're going to extract z-scores when we actually compute the scan statistic. So this data, actually, we're going to assume that it's a random measure. So you should think of this dx sup I as comprising the pixel values for the ith image. Right? Okay, and now, the idea is that if we want to do this in a multiscale fashion, we can dilate or expand this f. And this is a standard dilation operation here. Right? And this normalization factor maintains this L1 or this L2 norm being 1. Right? And so this is sort of important technical details. So the idea, because we're doing detection, we're going to ask the question, is the data only noise, or is there something actually going on? So is it business as usual, or do we actually see some signal F at some unknown location and unknown scale? Right? And more precisely, it's this additive noise model under the alternative. Right? And we're also going to assume that this is a d-dimensional Wiener process, and more generally, we can do a sub-Gaussian version of it. Okay, so the multiscale scan statistic, the idea is that we just convolve our dilated pattern with the image, and then we just see if that's abnormally high. Right? But we can choose many different scales. These are these h parameters. We can choose many different scales. So how do we deal with the fact that there's multiple scales? So first of all, there's a typo here. This n should be a capital L, so there should be no n here, just capital L's. So the idea is that we are going to select first a scale parameter, and then we're going to try every location for that pattern at that scale. And then we're going to say, let's convolve the image with that pattern at that scale. Say what's the largest this new field takes. And then we're going to remove some scale correction and multiply by the same scale correction. So the reason for this is, if we look at the form for the scale correction, this is L again, it gets larger as the image gets larger. That's natural because we're convolving more things and we're going to get larger maximums, right? But as the scale gets larger, so as this function gets larger, it's effectively there's fewer independent things, and so this max actually is getting smaller. Critically, what happens is we have to remove this location, but as the scale gets smaller, as this max gets larger, it actually concentrates more. It actually has a smaller standard deviation, which is why there's this multiplicative factor up here. Okay. So this is for a fixed pattern f, and this is the classical scan statistic with this multiscale correction. Okay. So what I'm interested in is actually if you have a database of images, or more generally tensors, can we learn what this pattern is, right? So the way we do this is we take our scan statistic for the given image, and for all of these images, we take an average, and this is a z-score variant, and then we maximize with respect to selection of this function, right? And so we call this a pattern-adapted multiscale scan statistic. Now, of course, because this function class, it can't just be anything. The issue is that if these functions are highly non-smooth, then a small translation is going to change significantly the statistics. So we have to control its smoothness. We have two ways of doing that. One is through bounded variation, and one is through this thing called an average holder condition. Okay. So one issue with this is that the scan statistic, if we would like to control this overall scan statistic, we would like exponential finite sample bounds for the scan statistic. But the scan statistic actually, it requires that the maximum is concentrating more tightly than we would get out of a standard result like Talleyrand's chaining, right, or the generic chaining. So to prove this, and this is a lemma for our purposes, to prove this we need a much more precise result, chaining result for sub-Gaussian processes. Right? And so the idea, we're going to assume that it has our space, which is induced by our Gaussian process. Our space has the following VC-type entropy bound. And what I prove in this theorem is that, in fact, the supremum of our Gaussian process, our sub-Gaussian process, it concentrates in a way that the location for this standardized sub-Gaussian increases, but actually it decreases in terms of the scale of the sup of the sub-Gaussian process, and it does so in an exponential fashion, so that we get that this scan statistic is a sub-exponential random variable. In fact, so the main theorem, we can just apply this with Bernstein's inequality and get that under the null distribution. The scan statistic can be controlled in a fashion that scales logarithmically with the size of our function class if the function class is finite. Doing chaining in this outer loop proved too difficult for this paper. It's future work. So we assume it's a finite function class. And the main takeaway from this, in terms of our power analysis, is that we get asymptotic distinguishability under the same conditions that we would get as if we assumed that the size of our function class was 1. Right? So that's the main point, is that we can do just as well as if we had a single function that we were scanning, even if this log number of functions increases almost like n. Okay, so that's it. Thank you, and you can see me at my poster.
Thank you. Are there any questions? Yes?
You said that you find it difficult to not assume that the class is finite, right? Function class.
Yeah.
Even if you assume other nice behaviors of the class, some covering, finite covering, stuff like that, stuff like that.
Yeah. So there's this interchaining that's going on because it's a max, a sum, and a max, right? So there's interchaining going on the first max. On the outer max, we would need to show that itself has some, in terms of the stochastic process that results from it, has some nice compactness properties. And it proves very difficult. But we can talk about it at my poster in more detail.
Thanks. I think we're short on time, so let's thank the speaker again.